Hello everyone. Today I'll be going over the rest of the polynomial topics that I didn't go over in Polynomial Part 1. So I already covered these topics, but today I'll be going over these ones. First, cubics. The most basic cubic is just x to the third, which looks like this. It differs from quadratics because, first of all, it is a odd degree polynomial. So its two limits as x goes to positive and negative infinity go in opposite directions. Obviously, this isn't the only cubic there is. Here's an example of one. And this is a much more typical cubic, I'd say. It has two bumps in it. And most cubics will have that. If you remember quadratics, they have one loop. This has two. And you'll notice one is called concave down, and then it transitions into concave up, where quadratics are only either all concave down or all concave up. And it's the same for this one. This is first concave down, and then flat, and then concave up. And here you'll notice quadratics have only one vertex. These actually have two vertices. Generally, cubics and most higher degree polynomials are more complicated and thus harder to make generalizations about. The generalizations that apply to all of them still hold, of course, but there isn't as clean of a vertex form, for example. But something to note about cubics and in general all odd degree polynomials, they will always have at least one real factor because they stretch from negative infinity to positive infinity, and so they will eventually cross the real number line. Here's the general formula for cubics. It's very similar to quadratics, but we just have an extra d where it's ax cubed plus bx squared plus cx plus d. Now we're going to talk about how to do polynomial division. We talked about how to do factoring, mostly for quadratics and a little bit for cubics in the previous video. But now we're going to talk about kind of general, using any polynomial, how would I factor it or divide it by another polynomial. So first, long division. This is the more general approach. It has the same reasoning behind it as normal division. So let's say we want to divide x cubed minus 2x squared minus x plus 2, and we're going to divide it by x plus 1. So with long division, the first thing you want to do is kind of check how many times this can fit into this first term. So we're really going to look at the highest degree here and the highest degree here. And so what can we multiply this by to get to this? So x to x cubed, we can multiply it by x squared. So then what we're going to do is we're going to multiply this entire divisor by x squared and subtract it to represent that we've taken out this times x squared. And then we'll simply do that subtraction. Obviously this part will cancel, and we'll be left with negative 3x squared. We'll bring down the rest of the polynomial, and then we'll do the same thing again. How many times can this highest degree fit into here? Or, in other words, what do we multiply it by to get it to here? And it's negative 3x. And so we'll multiply this by negative 3x and subtract it. And again, we'll get 2x. We bring down the rest. How many times does x fit into 2x? 2 times. And then we'll subtract 2 times this polynomial, and we'll get 0. This tells us that this divided by x plus 1 is x squared minus 3x plus 2 with 0 remainder. Synthetic division, the same polynomial and divisor. For synthetic division, what you'll do is for the thing you want to divide, you'll take the root of whatever this would be. So where this would be equal to 0. So the x value where this is equal to 0 is negative 1. And then for this, you'll just write down the coefficients. So -1, and then 1, -2, -1, 2. And then, now we'll actually start the synthetic division. First, with this first leading term, you'll just bring it down. And then the thing that's here, you'll multiply it here by this, and then add it to the next column. And then we'll add these two numbers together. And then we'll take this, multiply it by this number, and put it here. Then we'll add these two numbers, then take this number, multiply it by here, add these two numbers, so we get 0. And if this is a 0, that means there's no remainder. And we can convert back to normal polynomial form, and we get the same thing. If you notice, here we're doing -1 times x squared, and this is 3 times x, and this is 2. So the coefficients are actually the exact same, and this is kind of like a easier way and less convoluted way to do the division. But an advantage of long division is you can actually do more than just a binomial. So you could do like a cubic or a quadratic or however much you wanted to do, and you could still do this long division. But with synthetic division, you have to divide it by a root. You have to have a root that you're dividing by. Another thing is this could also be 2x plus 1, but here they would just represent as -1/2, because it's always the root, not the entire factor. And then with the remainder for both of these, obviously it was a 0 remainder, so it has a kind of a clean division. But if there wasn't a 0 remainder, you would simply have to add whatever the remainder was divided by x plus 1, or divided by the divisor. Now more about roots. So for any polynomial, the roots are the x values where the function is equal to 0, or the polynomial is equal to 0. And so a lot of what we want to do with polynomials is find the roots, which are associated with the factors. So if there's a factor of x plus 1, the root for that is -1. If there's a factor of x plus 3, the root for that is -3. If there's a factor of x minus 2, the root of that is 2. So given a polynomial with integer coefficients, we can apply the rational root theorem. So first we'll take the Cn is the lagging or the last coefficient, and C0 is the leading coefficient. And P represents all of the factors. So like 1, like if it's a prime number, it'll be 1 and that number, but if it's not a prime number, then it will be all of its factors. And that P represents all of the factors it could be, and Q represents all the factors of the leading coefficient. And then all of the possible rational roots will be P divided by Q, where P could be any of the factors of this, and Q is any of the factors of this, including positive and negative. So obviously for for very large numbers, this will give you a lot of possible roots, but you know that there is no possible rational number, so fractional number in other words, that could be the solution to this quadratic if it doesn't fall into this criteria. Now more about rational, real, and complex roots. So rational numbers are these, so any integer divided by any other integer, with the exception of divided by 0. Then real numbers is just any number in general. Something to note is the square root of 2 could be a solution with integer coefficients, but actually pi and e are something called transcendental numbers. So these are actually, they cannot be the solution to polynomials, unless they were and if it's x plus pi, obviously pi is the solution, but if it's x squared plus 3, x squared minus 3, I guess in that situation, the solution would be plus and minus root 3. But pi and e are unique real numbers, as they can't be the solution. But any root That's why these are called the roots, because they are the root of polynomials. And then complex numbers have a imaginary and a real component. Imaginary numbers like zero real component can also be solutions to polynomials. Generally, they fall into the complex category. And something else to note is that a polynomial with real coefficients, all of its complex roots will come in pairs. So a plus bi, if that is a solution, a minus bi will also be a solution, no matter what. Finally, Descartes' rule of sign, using the same polynomial we solved in the previous slide, we can actually find out the maximum number of possible positive and negative roots. So first we'll look at the signs of these. So this has positive, negative, negative, positive, and then we'll count the number of consecutive sign changes. So it starts positive, it goes negative, that's one sign change, it doesn't change, changes back to positive. So that's two sign changes. And that tells us the number of positive roots is 2, and because it's a cubic, there are 3 total roots. It means the number of negative roots will be 1. But as I said before, complex roots, this does not account for complex roots, and they can come in pairs of 2. So technically, this could be 2 or it could be 0. But since we can't take 2 out of 1, this has to be one real root. So either there's 2 positive roots and 1 negative root, or there's 0 positive roots, 2 complex roots, and 1 negative root. Also goes through some bonus factor methods you can do. So substitution, let's say we had this polynomial and we wanted to factor it. We don't know a specific method for factoring quartics or 4th degree polynomials other than guessing and checking with syntactic division or long division. But if you notice, if you have this kind of format where it's a trinomial and each of these are even, or more specifically, the power of this is double the power of that, then what you can do is substitute x squared for w. We can rewrite it as w squared plus 2w minus 3, and then just solve for w, or factor it in terms of w, so it would just be this, and then put x back in to get us here, and then if we need to factor it further, we can. So first we could factor this x squared minus 1, that's difference of squares. And then here, we couldn't technically factor it into real numbers, but we could factor it into imaginary numbers. So this would get us x plus the square root of 3i and x minus the square root of 3i times x plus 1 times x minus 1. There's another method called factor by grouping. So if we're given this situation and we notice that the coefficients kind of match each other, where this is times 3 and this is times 3, the coefficients, then we can factor out an x squared out of here, leaving us with x plus 3, and factor out a negative 4 out of these two terms, leaving us with x plus 3. We notice, oh, now this x squared and this minus 4 have a common factor of x plus 3. We can factor it out, and we're left with x squared minus 4 and x plus 3, and we can factor it further by factoring this x squared minus 4 with difference of squares. We can also do this even if we're not explicitly given kind of this coefficient ratio. If we're given just a normal quadratic or any degree polynomial, and we can split it up into that form, we can still apply it just the same. Now, if we're just given points that we'll kind of want to weave a polynomial through, generally, if you have 3 points, we would want a quadratic or a trinomial. So it would have quadratic has a a, b, c with the ax squared plus bx plus c. So with 3 points, you're going to want 3 things you can change. 4 points, you would want 4 things you can change. If we're given 3 points, technically we could have a quadratic or higher, but then we would have kind of too much freedom. So we might have to invent a point that we want to also put on there. Generally, if you want to have a specific polynomial go through these points, the best thing to do is have the degree 1 less than a number of points. So when we want to find the actual equation, we'll simply, given this y equals x squared plus bx plus c, we'll substitute these points into this equation. So for example, we could substitute -1 in for x and -4 into y. And we can do that for all of these points, like so. And now the only unknowns are the variables themselves. So if you're observant, you can see this is 0, so you could actually just tell that c is 2 from this point. But we could also just use system of equations. So we could subtract from this equation, and subtract from this equation, leaving us with this, and then do the same thing. And then we'll see, oh, a is -2, b is 4, c is 2. That would be what the polynomial is, and we can graph it, and we see that it goes through all of those points. Right now we're going to talk about function transformations in terms of polynomials. So function transformations aren't necessarily a polynomial category, but they do have a very useful vertex form analogy. So hopefully you're familiar with a vertex form, where this would be h would be the x position of the vertex, and k would be the y position of the vertex. And then a would be kind of the stretch factor. And if we move k, the entire graph would move up or down. If we move h, the entire graph would move left or right. If we move a, or change a, the entire graph stretches up and down. And this can apply to function transformations. So let's say we had a function that's equal to x squared. If we have another function that's equal to some function transformation of that, this is just the exact same thing as vertex form. So here, this represents -2h, so that means we move 2 to the left, and then this is a -1k, so we would move down 1, and then 2 means it would be stretched up by a factor of 2. Something to note here with function transformations is everything outside of these parentheses follow normal order of operations. So you would scale it by 2 first, and then subtract 1. But here, you notice that it says plus, but we're actually moving to the left. And the reason is inside these, we actually use inverse order of operations. So we kind of have to imagine we have something that this is equal to. So x plus 2, we would subtract 2, and that's what would happen. So we kind of want to get back to x, and to do that, we would subtract 2. Finally, modeling with polynomials. It's very common to model the path of a projectile with a quadratic because the path of a projectile follows a parabola. There are other modeling things you can do with cubics or quadratics or whatever you want, but probably the most common is a parabola. So generally, you just use your knowledge of quadratics to help you with this. Something important is kind of the axis of symmetry is very important, and for any two x values that have the same y value, their exact center will be the axis of symmetry, and on that axis will be the minimum or the maximum. Generally with modeling projectiles, it will be the maximum, kind of the highest point. And in this case, the x-axis could be time or distance. So let's say, it takes something 6 seconds after I throw it, it takes 6 seconds to land. At what point, at what time is it the highest? And we would know it's 3. But you could say, I throw something and it lands 6 feet away from me. At what distance from me is it the highest? The same answer would be 3 feet. And along with my previous polynomial video, that's pretty much everything you need to know with polynomials. Comment below if you have any questions, and thank you for watching.